Okay, so following on from last lesson, we're going to just keep adding to these differentiating techniques that we've already got. So we've learned the power rule, we've learned the chain rule, and today we're going to add another little tool to our toolbox, and that's going to be something called the product rule. So let's have a look and consider this example here. Y equal to x squared in brackets x to the power of 5 plus 1. Now up until now, we've only been dealing with the derivative of a sum of terms. So for instance, if we have one function plus another function. So as an example, we could have d by dx of, let's say, x squared plus 2x. Okay, and we know we can use the power rule on these because the derivative of the sum is just equal to the sum of the derivatives. So this would just be 2x plus 2. Okay, so going back to our first example, what we could do is we could expand both or the bracket out, and we could get x to the power of 7 plus x squared, and then we could just differentiate this. So we could say, well, what's dy on dx of this term? So using the power rule, we would get 7x to the power of 6 plus 2x. Now, what if these two functions were more complicated, right? Something that we couldn't expand. Maybe one was under a square root. So we have to possibly consider that maybe these are two functions that we can't expand out, and we can maybe call the one u and the one v, so we have one function multiplied by another function, okay? So in other words, we have a product. So what about products? Do they differentiate the same as a sum? Can we just differentiate each of them separately and then multiply them together? Will that give us the correct derivative? Well, let's just take a simple example, right? Let's take 5x, okay? Let's say one of the functions is 5 and one of the functions is x. Those are my two functions and they're being multiplied together. So let's pretend that this is how the way things do or happen. So we take the derivative of one multiplied by the derivative of the other, and we know the derivative of any constant is just 0. And the derivative in this case of x is just 1. So 0 times 1 is equal to 0. But we know that the derivative of 5x using the power rule is 5. So clearly this is not the way that we differentiate products. So we need to come up with a better technique. And the way we learn all new rules is by thinking about them in terms of first principles. So we'll come back to this and we'll put the correct equation there. But let's go and consider how we would calculate the derivative of a product. So it helps to start by saying, well, what is first principles? Well, it says that the derivative of some function is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And remember, we chose what h was, so we're making it smaller and smaller. Now, I've got f here, but f could be any function. It could be q, it could be t, it could be u, it could be v. And that's exactly what we're going to consider now. Let's say we have some function f of x, okay? And it's made up of two functions. So let's call them u of x and v of x, right? So they could be like our original one, x squared, and v of x could be x to the power of 5 plus 1. It doesn't really matter. And we want to find the derivative. Okay? So what we're going to do is we're going to use first principles. So first principle says if we want the derivative, the gradient function, that's equal to the limit as h approaches 0 of u, but not of x plus h times v of x plus h, and then we're going to subtract the original function. So u of x, v of x, right? And all of this is over h. All right, now at this point, it might seem like we can't do anything, but a lot of times in maths, by using a bit of manipulation, we can move forward. And so what we need to do is we need to change this function slightly, right? Remember, we can't change it because it's an equation, but we're going to manipulate it in a certain way. So I'm going to add and subtract the same thing. So that's the overall effect is I'm doing nothing. So I'm going to add a special term so that we can carry on working out what this derivative is going to be. So what I'm going to do is I'm going to subtract u of x plus h v of x, and then I'm going to add it straight back. So plus u x plus h v of x. And then we still have our subtract u of x v of x at the end there. And this is all still over h. Okay, now you'll see I can factor certain things out of the first two terms. So what I'm going to do is I'm going to pull out u of x plus h, and what's left over is inside this bracket we have v of x plus h minus v of x. Alarm bells should be ringing at this point. Okay, and then I'm going to do the same thing in the next one. I'm going to pull out a common factor, and this time what I'm going to do is pull out v of x, and what's left over is going to be u of x plus h minus u of x, and all of this is still over h. Okay, now I've got two terms added together by a same denominator, and what I'm going to do is I'm going to split them back up into separate terms. Okay, so I'm going to separate the terms from here into two separate terms. So we'll have u of x plus h, and then we have this v of x plus h minus v of x all over h. And then I'm going to do the same thing here. I'll have v of x, and here I have u of x plus h minus u of x, and this is now all also over h. Now, when we assess limits, the same thing applies with derivatives. So the derivative of a sum is just the sum of the derivatives. So the limit of a sum is just the sum of the limits. In other words, I can assess these two things separately. Okay, so that's what I'm going to do. I'm going to assess the limit of each of these different components separately. And you'll notice that this is being multiplied by this, all right? So I can sort of split them apart because they are three separate terms. Okay, so I'm going to have here the limit as h approaches 0 of u of x plus h times the limit as h approaches 0 of this v of x plus h minus v of x all over h. I'm going to do the same thing with the other term. So we have plus the limit as h approaches 0. I'm going to split this v of x off and then multiply it by the limit as h approaches 0 of this u of x plus h minus u of x all over h. So at this point, we are ready to assess our limits and actually figure out what's going on here. Okay, if we have a look at the first term, we have the limit as h approaches 0 of u of x plus h. So if we put values into h, right, as they get smaller and smaller and smaller and smaller, h tends to 0, and so what we're left with is just u of x. Now the next one, as we have the limit approaching 0 of this, you'll notice that this is exactly the same as our formula for first principles. Derivative of f of x is equal to the limit of f of x plus h minus f of x, except this is just v. So what we've basically got here, the limit as h approaches 0, is the derivative of v. So we're multiplying by v dash x, so the dash, the derivative. Okay, and then we've got this limit as h approaches 0 of v of x. There's no h's in there, so v of x doesn't care, so we just have v of x, and that's multiplied by the limit as h approaches 0. This time you'll notice that this is the formula for first principles in terms of u, and so this is just u dash of x. And so what we've got is, if we want to calculate the derivative of a product, we basically take the first function and we multiply it by the derivative of the second function. And then we take the second function and we multiply it by the derivative of the first function. And that is our formula, or our rule, for differentiating products. Now, there are many different ways that you will see this being written. So I could have also written this as u, the function u, times the derivative of v, which would have been dv on dx, because you remember we're differentiating everything with respect to x. And this would be plus v times the derivative of u with respect to x. Okay. Now, the way I find it easier to remember, and it ties in very nicely with the quotient rule that we'll learn later on, is to remember it like this. V u dash, so v times the derivative of u, plus u times the derivative of v. And what we get here is what we say vuv. Okay, and you'll see why it's quite nice when we learn the quotient rule. So I like to remember it like this, but you can remember it in any form. Okay, so we can formalize this, and we can say we've just discovered that the way we derive products is we take the one function and we multiply it by the derivative of the other function, and then we add that function and multiply it by the derivative of the other function. Okay, and as I said, you can remember this as v u dash plus u v dash to make things easier. Okay, so let's quickly have a look at our silly little example here of the derivative of 5x and see if this works. Okay, so we have, using the product rule, we have, if we always need to call one function u and one function v, so I'm going to call them u and v. So I'm going to take v, which is x, and I'm going to multiply by the derivative of u. U is just a constant, so its derivative is 0. And then I'm going to add u, which is 5, and the derivative of v. When I differentiate x, I get 1, and so we get 5, and we know from the product rule that that is correct. Okay, we can also use our original example of y equal to x squared, x to the power of 5 plus 1, and let's use the product rule to differentiate. So we want to find dy by dx. So we remember the rule, v u dash plus u v dash. So I need to call one u and I need to call one v. I'll call this u and I'll call this v. Now remember, when we differentiated with the power rule, we got 7x to the power of 6 plus 2x. So we expect to get something exactly the same. Okay, so we take v. So v is x to the power of 5 plus 1, and we multiply that by the derivative of u. The derivative of u is just 2x. And then we're going to add u, which is x squared, and we're going to multiply that by the derivative of v. So v is the inside, is in this bracket here, so its derivative will be 5x to the power of 4. So just expanding these out, we're going to get 2x to the power of 6 plus 2x plus 5x to the power of 6, which can simplify into 7x to the power of 6 plus 2x. So that's exactly the same as what we got using the power rule.